graphs. So these are some of the common features that we look for in graphs to help us graph them or to determine some of the characteristics that will give us more information. So the first thing we do commonly is find intercepts. You have done all of this before. So we're just going to try it with these two random equations. Okay, if I want to find the y-intercept, that's where where the graph intersects the y-axis. So I always set the x equal to 0, and this is true regardless of whether this is a function or not a function. Okay, I would make the substitution. So when I plug in x equals 0, I get y equals square root of 5. So the y-intercept is at 0, comma, square root of 5. And then I'm going to go ahead and calculate the x-intercept. The graph will intersect the x-axis when the y value is equal to 0. So anytime I want the x-intercept, I substitute as 0 in for the y variable. Okay, then I'm going to go ahead and solve this. I'm going to square both sides to cancel out the square root. So I found x equals -5 when y is equal to 0. So the x-intercept is -5, comma 0. It is possible for there to be multiple intercepts, x or y intercepts, and there's possible for a graph to have no intercepts. Okay, I'm going to do the same process with the relation y squared equals 9 minus x for part B. So again, to find the y-intercept, I just have to let the x-coordinate equal to 0. Because the y is squared, this is a quadratic. I'm expecting I will most likely get two values because it's degree 2, and I will. It's y equals positive and -3. So the y-intercepts are at 0, 3, and also at 0, -3. Then the x-intercept, I'll go ahead and substitute in 0 for the y value. And you don't have to write x equals 0, y equals 0 every single time. Okay, so if I plug in 0 for the y value, I get 0 squared, which is 0 equals 9 minus x. I'm going to add the x to the other side, and I get x is 9. So the x-intercept occurs at 9, comma 0. So this particular graph has 3 intercepts, and if it just asks me to find the intercepts, they do assume that you're going to find both the x and y intercepts, assuming your equation has 2 variables. The next characteristic of graphs that we like to look at is their symmetry, and we normally look at their symmetry with respect to the y-axis, the x-axis, and the origin. I'm going to sketch a graph so you can see what each type of symmetry looks like, so you can see that the algebraic test relates to the picture when we examine the picture. The y-axis is this thing right here, if I had drawn my graph perfectly. So if this function has y-axis symmetry, the other half should be a reflection. Something like this would make sense. If I were to examine a point on one side of the y-axis, say this random point right here, I'll call it x comma y, there will always be a reflected point across the y-axis over here. This point would be -x comma y, and that's true of any random point I pick along this function, assuming it has y-axis symmetry. Okay, if it has x-axis symmetry, it's going to reflect across the x-axis, so something like this. And the relationship I'm looking for is if I pick a random point x, y, the symmetric point across the x-axis down here will have the same x-coordinate, but the y-coordinate will have the opposite value, so I'll call it -y. Okay, the third type of symmetry we're going to look at is origin, and the symmetry with respect to the origin is rotational symmetry. So if I took this and rotated 180 degrees, it would end up going over here. Okay, and again, I'm going to consider a point and then consider the reflected point. So if this was some random point x, y, if I go over here to quadrant 3, this point will now be -x, comma, -y. And as long as you keep those images in your head, then the algebraic test for symmetry follows directly from that. Okay, so we're just going to try the algebraic test for symmetry with one function. This happens to be a function, but this would work for any type of relation at all. Okay, so it says test for symmetry. That means y-axis, x-axis, and origin, and the order I go in doesn't matter. So say I want to check the y-axis symmetry first. Okay, to check for y-axis symmetry, I'm looking for if I plug in negative xy, or if I plug in negative x, the resulting y value will be the same as if I plug in positive x. Okay, so I'm going to make a note that I'm going to plug in negative x and keep the y positive, and I should end up with the same equation I would have ended up with otherwise. So I'm keeping the y the same. Where I see the x, I'm plugging in negative x. And then I'm hoping it ends up in the same equation for y, because that would mean it ended up in the same coordinate. Negative x to the fourth is positive x to the fourth. Negative x squared turns to positive x squared. The plus 1 stays the same. And because this function matches this function, this is symmetric with respect to the y-axis. Okay, just because it is symmetric with respect to the y-axis doesn't mean that it cannot also be symmetric with respect to the other types of symmetry we could have. So I'm going to go ahead and check for x-axis and origin. If I'm checking for x-axis symmetry, I'm both going across the x-axis, so the y is changing signs. So I want to see that when I plug in x, I get negative y, and it results in the same equation. So back to the original function over here, I'm going to plug in the same x value, but I'm going to make it a negative y, and see if I can't make this equation revert to its original state. Okay, say I want to solve for y. I'm going to divide everything by a negative. Okay, now if I look at this and this, these don't match, so there is no x-axis symmetry. Okay, and then the last type of symmetry I'm going to check for is the origin symmetry. Okay, which means I'm going to check that if I plug in negative x and negative y, can I turn it back to the equation with positive x and positive y? Okay, I'm going to go ahead and divide the negative over so I can isolate the y. And we can see again, this I can't convert this to the original equation, so there's no origin symmetry in this case either. Okay, so the only symmetry that I see in this for this particular function is it is symmetric to the y-axis. Most graphs are not symmetric to any of them. They're just a random graph in space, so the fact that it has symmetry is special. It is possible to be symmetric to more than one. An example would be a circle centered at the origin. That would be symmetric to the y-axis, the x-axis, and the origin. So you should check for symmetry in all directions, even if you found that it does work in one direction already.